Hello students. Today we are going to learn about one component system. And to understand this one component system, we are going to take the help of the phase diagram of water. Now, if I am asking what is the boiling point of water, so what would be your answer? Definitely it would be 100 degrees Celsius, right? And what if I am asking the freezing point of water? Yes, you are right. It is 0 degrees Celsius. But is it true in every condition? That is my question. So we will solve this question by studying this phase diagram of one component system. Now look at this diagram. We have plotted a graph of pressure versus temperature. Pressure is on the y-axis and temperature is on the x-axis, and you can see three different areas which are being separated by three different curves. Curve OC, curve OA and curve OB. Okay, now let us study the areas first. So if I'm looking into the area COB, in this area you can see water is in solid state. That is, in this area you will see ice over here. Similarly, in the area COB, in this area the water would be present in liquid state. Okay, and in the area BOA, here the water would be present in gaseous state. So you can see the three different states of water: solid ice, liquid water, and the water vapors, which are being separated by the three different curves OA, OB, and OC. Now, if I'm looking into the curve OC, so here this curve separates the solid water and the liquid water, right? So I can say that on this curve, solid water is in equilibrium with liquid water, right? Because solid is getting converted into liquid, or we can say that the liquid is getting converted into solid ice. So the process is known as freezing or melting. Hence, the curve is labeled as freezing curve or melting curve. Okay, similarly, you can see the curve OA. Here, liquid water is getting converted into gaseous water, that is water vapor. And this process is known as vaporization. Hence, the curve is labeled as vaporization curve. And over here, curve OB. Now, here the solid water, that is ice, is getting converted into gaseous water, water vapor directly. And this process is known as sublimation. Hence, the curve OB represents the sublimation curve in this phase diagram. Okay, now our phase diagram is plotted between pressure and temperature. Now, the place where we are sitting, if I am asking what is the pressure over there, so your answer would be 1 atm, right? So, if I am considering pressure 1 atm at this point, and if I am extending this line, so you can see it will meet the curve, freezing curve, that is OC at this point. And if I am extrapolating this line towards the temperature axis, it will meet a certain temperature, and this temperature would be 0 degrees Celsius. Why? Because the freezing point or the melting point of water is 0 degrees Celsius, right? Now, if I'm further extending this line, so it will meet the curve OA over here. Now, OA is our vaporization curve. Vaporization means liquid getting converted into gaseous water, and if I am extrapolating and extending this line towards the temperature axis, there would be a certain temperature, that is 100 degrees Celsius. Why 100 degrees Celsius? Because this point is known as the boiling point of water. Now you can observe that at 1 atm, that is, if the pressure I am maintaining 1 atm, the boiling point would be 100 degrees Celsius and the freezing point would be 0 degrees Celsius. Now, what if I'm slightly increasing the pressure, and let us assume now our pressure is 5 atm. Now, what do you think? Will be the boiling point and freezing point be the same? Let us see. So 5 atm, I am again extending this line. It will meet the freezing curve. And if I am extrapolating this to the temperature axis, so you can see that it is not meeting at 0 degrees Celsius now. Similarly, if I am again extending this line to till the vaporization curve, and if I am extrapolating it towards the temperature axis, now it is also not meeting the boiling point, that is 100 degrees Celsius. So what we can conclude over here, that the boiling point of water, which we are telling it as 100 degrees Celsius, and the freezing point of water 0 degrees Celsius, this is applicable only when the pressure is 1 atm. If I'm slightly increasing the pressure or decreasing the pressure, the boiling point, that is the temperature, will also increase or decrease accordingly. Okay, so to understand this, we are learning this phase diagram. Okay, now you know the answer that the 0 degree Celsius and 100 degree Celsius temperature is only applicable whenever the pressure is 1 atm. Okay, now we have learned something called the degree of freedom, right? So let us calculate the degree of freedom over here and let us learn why we are calculating this degree of freedom and what is the use of it. Okay, I hope now you have understood the phase diagram of water. Now let us move towards different examples and learn how to calculate the degree of freedom. Okay, now you can see a point over here, the blue colored point, and let us say that this is our system. This point is our system. Now the system is under the area AOB. Now under the area AOB, you know that the water is existing in gaseous state, right? So chemically, if I have to write, I can write it as water in gaseous state is present in our system. Now, if I have to calculate the degree of freedom at this particular system, so you know, first we need to calculate the number of phases. So over here, you can see only gaseous water. So the number of phases would be 1. Now, similarly, components. Since we are studying one component system, so definitely C would be 1. Other than that, you can see that only water is present. Other than that, no other component is present in our system. So the number of components 1, and you know how to calculate the degree of freedom. F is equal to C minus P plus 2. So 1 minus 1 plus 2. So it is coming out to be 2. Hence we can say that our system is bivariate. Now, what is the meaning of bivariate and what is the use of this value 2? Now let us see. If I have to check, or if I have to say or define that my system is exactly at this point. So what all variables you will require? If I am mentioning only the temperature, that at this particular temperature you are having the system. So if you are only know the temperature, you can say that the system might be here, it might be here, it might be here, here. Okay, in the single line you can plot anywhere, right? But our system is exactly here. How you will know? Only when I am mentioning the pressure, that at this particular pressure and this particular temperature, your system is present. So over here, you require the pressure as well as temperature. Both the variables were required to define this particular system. Hence, the two value indicates that to define this system, you will require two different variables, that is temperature and pressure. Hence, the system is bivariate. Understood. So F is equal to 2. The degree of freedom indicates that how many variables would be required to define a particular system. Similarly, in this way, if our system is at this particular point, so again your F value will come out to be 1 because the number of phases is same, water in liquid state. Components 1, hence the degree of freedom will come out to be 2. Again, if I'm saying the system is at this particular point, so you can say that here solid ice is present. So chemically, I can write as water in solid state is present at this point. So number of phases 1 because only solid is present. Number of components again 1 because only water is present. So 1 minus 1 plus 2, you will get again 2. So in the areas, at any point in the areas, you are going to get the degree of freedom as 2. Okay, now let us understand the different system. Okay, so now our system is exactly on the curve OC. Okay, so chemically, if I have to define this system, now you can see that our water is present in solid state at this area and water is present in liquid state at this area. Right. So here at this curve, what we can say that both these systems, both these phases are in equilibrium. Not systems, both these phases are in equilibrium. So if I have to write this chemically, what I can write, solid water, that is ice, is in equilibrium with water in liquid state. Okay, so because why I have written this? Because our system is exactly on this curve OC, and OC curve is the melting curve or freezing curve. Now, if I have to calculate the degree of freedom, how many variables would be required to define the system? So, first of all, you will require number of phases. So, over here you can see the solid ice and the liquid water. So, two different phases. So, number of phases 2. Number of components 1, because only water is present. Now you know the formula for variance. F is equal to C minus P plus 2. So 1 minus 2 plus 2, it is coming out to be 1. Hence, our system is monovariant in this case. Now monovariant indicates that either temperature or pressure would be required to define this system. Let us understand how. Now our system is this, right? So if I'm only mentioning the pressure, you can exactly point out that your system is at this particular point. Or you only know the temperature, you can exactly point out that the system is at this particular point, and simultaneously you can also say what would be the corresponding pressure or the corresponding temperature, right? So either of the one variable would be required to define the system, hence the value of f is coming out to be 1. Okay, so the system is monovariant at this particular point. Now let us understand this curve. If you have understand, you can calculate it on your own by pausing the video. So over here, you can see that the system is exactly on the curve OA. Now OA curve represents the vaporization curve. So vaporization curve means that the liquid water is in equilibrium with the water vapor that is in gaseous state. So these two states are in equilibrium. So chemically, I can write this system as water in liquid state is in equilibrium with water in gaseous state. So this is our system right now because our system is exactly on the vaporization curve. Now, to calculate the degree of freedom, first of all, the number of phases you have to calculate. So you can see the liquid state and the gaseous state. So two different phases. So number of phases, 2. Number of components, 1, because ultimately we are studying one component system. Other than that, you can say that only water is present. So the number of components is 1. Now F is equal to C minus P plus 2, which is the formula to calculate the variance. So 1 minus 2 plus 2. Again, your system is coming out to be the monovariant system. So here also you will require either pressure or temperature to define this system. Okay, either temperature you need to specify. You can tell what would be the pressure, or if you are specifying the pressure, you can say about the temperature. Okay, so any one of the variable would be required to define the system, hence the system is monovariant. Now, once again, on the curve OB. So OB curve is our sublimation curve. So if the sublimation curve is having this system, so if you have to define the system, so first of all, you will write chemically how to write the system. So here you can see that on the OB curve, the solid water, that is ice, is in equilibrium with water in gaseous state, water vapor. Now, to calculate the degree of freedom, you will require number of phases. So, ice and water vapor, two phases. So, number of phases 2. Components, definitely 1 because only water is present. Now, to calculate the variance, F is equal to C minus P plus 2. 1 minus 2 plus 2. Again, you are going to get the system as monovariant because the value of F is 1. So, here also either pressure or temperature would be required to define the system. You either tell me the pressure, I will tell you where the system is, or you either tell me the temperature, I will tell you where the system is. Okay, so here also to define the system over here, you will require either pressure or temperature. Okay, hence the system is monovariant. So with these examples, what we can conclude, if our system is exactly on any of the curves, okay, any of the curves, if you are having the system would be monovariant. So either pressure or temperature would be required to define that particular system. Okay, now let us check out this special point. Okay, so here you can see that all the three different curves are meeting at a particular point called O. right? The freezing point or the melting point, we can say. So the freezing point, the vaporization curve, and the sublimation curve. Okay, the freezing curve, vaporization curve, and sublimation curve. All these three curves are meeting at a particular point called O, which is called the triple point, a special point where all the three phases are in equilibrium. So, since our system is at this exact triple point, so if I have to write chemically this system, I can write it as the solid ice, that is water in solid state, is in equilibrium with water in liquid state, and this is further in equilibrium with water in gaseous state, which is our water vapor. So this is our system where all the three phases are in equilibrium. So to calculate the degree of freedom, again you will require the number of phases. So number of phases, it is 3, because you can see solid water, liquid water, and the gaseous water are in equilibrium together. So the number of phases 3, number of components 1, because only water is present in our system and we are also studying one component. So definitely the value of C would be 1. Now to calculate the degree of freedom also known as variance, we know the formula F is equal to C minus P plus 2. So 1 minus 3 plus 2, it will come out to be 0. So in this case, our system is non-variant. Now, what is the meaning of non-variant? We don't require any of the variable to define the system. Neither pressure is required, neither temperature is required in this case. You can directly point out if all the three phases are in equilibrium and if your value of F, that is variance, is coming out to be 0, then you can clearly say that the system is present at the triple point, because in the phase diagram of water, only one triple point is present. So directly you can point out that the system is at the triple point. Neither temperature is required, neither pressure is required to define the system. Because if your value is coming out to be 0, you can directly point out that my system would be at the triple point. Okay, so over here, if I have to conclude about the one component systems, so we have seen areas, three different areas which were having water in solid state, water in liquid state, and the water in gaseous state. Then we have seen three different curves. That is the freezing curve, which is also known as the melting curve, where solid water and the liquid water were in equilibrium. Then we have seen the different curves like vaporization curve, where the liquid water and the gaseous water are in equilibrium. Similarly, we have seen the sublimation curve, where the solid water, that is ice, is in equilibrium with the gaseous water. And we have seen a special point called triple point, where all the three phases are in equilibrium. Okay, so if I have to conclude them, so what would be the degree of freedom? So at any point, if my system is present on the areas, the degree of freedom will come out to be 2. At any point, if the system is on the curves, then your degree of freedom will come out to be 1. And at the special point, triple point, your degree of freedom will come out to be 0. So if F value is coming out to be 2, hence the system would be bivariant, where you will require pressure as well as temperature to define the system. Hence, we are calling it as bivariant. If the system is present on the curves, then you will require either pressure or temperature to define that system. So, hence, the system would be monovariant at that point, and at triple point, neither pressure nor temperature is required at that particular point, because triple point is present only one in a particular phase diagram of water system. Hence, you can directly point out the triple point where it is, where all the three phases are in equilibrium. And hence, directly you can say that my system is at the triple point. Hence, neither pressure nor temperature is required to define that particular system.